Welcome to the pre-recording of lecture 34 in a course on supercomputing. It's Introduction to Supercomputing, and we are also starting another chapter today with this lecture, and it's a chapter on applications. So in a way we are starting in a completely different way than the high performance angle. We are looking at applications, here in particular the Fast Fourier Transform and sorting. At first, these two things don't seem to have anything in common, but we know that both problems have a complexity that is quasi-linear, in particular n log n. So that unifies these two. Also, we will take, as I said, the angle of software, and in this part of the course we are heavily intersecting a course on scientific software, where actually we don't really look to implement everything ourselves, but we look for excellent software that is out there. And we start with the fastest Fourier transform in the West, known as FFTW. But to make it self-contained, let me explain what the Fourier transform does. It maps a signal, so signal is continuous in time, but we have samples, we have numbers on input, a discrete set of numbers, and then the discrete Fourier transform maps the numbers from the time domain into the frequency domain. Here is the formula. So if you are, it looks a little bit scary, but if you are familiar with complex arithmetic, it is very straightforward, immediately to implement. However, if you do it according to the formula, then it will cost you n square operations. Which means that if you double the size of the input, the time you will have to wait for the output will be quadrupled. With n log n, this is significantly less. So think about 2 to the power 10, 1024. Then the time is 10,000 and not 1,000 times 1,000. So there is a significant reduction by using the fast Fourier transform. So the fast Fourier transform has many applications, in particular signal processing and image processing. I will not explain what is the fast Fourier transform, but immediately go to the software. So the FFTW received the Wilkinson Prize for numerical software. I checked, the version is still 3.3 point something. So the software is very stable. And what is important for us here is that it enables message passing and OpenMP and a multi-threading. So if you are installing this in your computer, here is the configuration at which you should install it, especially with the context of this course. Okay, so in this course we have covered OpenMP pthreads, not really Silk, which is now an extension of the C programming language, but for the purpose of this course and also for the application, it's mainly important that we can apply the software. So here is what it does. In the time domain, we have a test signal of two components running at two different amplitudes, 2 and 5, and two different frequencies, 4 and 10. So if we look at the definition of the function, we recognize this, but the magic of the fast Fourier transform in the translation from the time domain to the frequency domain, the magic of the Fourier transform is that it will enable us to capture the essential components from the signal, simply from the numerical data. So if you look to the plot in the time domain, it's actually not really obvious. So you could see that this goes between -7 and 7. So if you sum the two amplitudes, and you can kind of see that it's not really a pure sine, so there are different wobbles in there depending on these frequencies, but it's hard to tell from the picture in the time domain what the main characteristics are now of the signal. Alright, C is the common language that we are using still in this course, although there are wrappers if you want to use it in Julia, no problem there. So there is the FFTW package. Also Python has wrappers. So, but I will explain it here with C. For convenience, we will take a number of samples that is a power of 2. So we have the data that is generated by the mySignal function. And here is then the main C program, mainly to indicate that it's not that difficult to use. So we have the making of the signal. So the first, of course, the allocation of the data, and here we work with 256 samples, very modest. We allocate, so as was clear from the formula, we actually compute complex numbers, so we go from the real to the complex. So there is an FFTW complex. How the data are represented is critical here. So there is a plan. I will try to explain what is the plan, and then there is the execute. So, and this is essentially it, because after that you can extract the output from the data that is computed by the execution. So the entire C program, the main program, actually doesn't really take long. So we have the input, the X and the Y, and then the output. And actually the processing of the output takes more code here than the calling of the routines. So this is used in filtering. So on the output numbers, I compute the magnitude of each number. So this is where the V comes in, and all the numbers that are less than the tolerance are suppressed. And it will turn out that only 2 numbers will survive, and these are the 2 numbers that the numbers there, the 2 corresponds to the 2 components of our test signal. So here is what comes out. So we see that at amplitude 4, we see what is the frequency, and the frequency, sorry, we have if you would plot, and I don't think I have made a plot, I should have made a plot, but in C it's rather difficult. Well, it's not difficult, it's not as straightforward, but I'm digressing. Here we have 2 components, remember, in the test signal, one with frequency 4 and amplitude 2, and another one at frequency 10 and amplitude 5, or 2 and 5 are the amplitudes, 4 and 10 are the frequencies. So this is just a very simple test. Also, if you use a makefile, you have to link with the library. And here the installations happened as super user. So if you install it on your own user account without the proper privileges in a special location, then you may have to twiddle a little bit with the linkers. But other than that, it is very straightforward to use this software. Okay, Let's do the shared memory implementation. We have enabled OpenMP. So in order to test the speedup, I will allow that the user can specify the dimensions. So here you see that the first argument, or the argument at position 1, has the dimension, and then there is a second argument that will indicate the frequency of the run. So if that argument is not provided, then the default will be 1. So this is for timing purposes. I do not want to prompt or fix the number of the dimensions of the problem in the code itself. Okay, so let's now look at the modifications to start using the OpenMP. So we have again the data set. We will run it. We create a plan and we time it. So we compute the CPU time. That was the sequential version. Now let's do the third argument, the number of processors. We will initialize with the number of threads, and then with OpenMP we set the number of threads. The plan is executed with the number of threads, and that's the main modification to the code. So here you see the running. So the speed up on a 16-threaded computer, twice 2 cores, twice 8 cores. You see we have a very good speed up at 2, even at 4 it's quite good. It starts to taper off a little bit. We see the wall clock time, and I think the wall clock time was used to compute the speed up. At least this is what I hope so. And then we have the system time. So we use more system time with the, yes, I used I used actually the wall clock time. So you see that the other time is actually, the user time is actually not useful here. For obvious reasons, because the user time goes up, and this counts here the total CPU time. It's not the reported clock time. If we are wanting a better speed up, then we should actually see run this for larger dimensions. So here for 1 million. And now you see that we can have super linear speed up. When we have a multi-processor machine, we have actually also better facilities to process more memory, more caches available. So in some sense we have mentioned superlinear speed up in the course already early on in the first lecture, I remember. But here is a manifestation of superlinear speed up. You get this for 1 million. Also doing sufficiently many times. So we do 1000 discrete Fourier transforms. And the wall clock time drops dramatically. So great. Okay, so I will list the main reference at the end of this lecture. Here is what I got from why the Fast Fourier Transform is so efficient. In a nutshell, it compiles the code. It generates what are called codelets. It generates code specific for the processor, for the type of processor. So it has a special purpose compiler specifically dedicated for the operations that are used in the Fast Fourier Transform. And sorting is also used there. Radix sort is mentioned. So in some sense, the connection with sorting is not at all far-fetched here. And actually, for simplicity of algorithms, I should have covered sorting, of course, first before the Fast Fourier Transform, but it also involves some sorting. So all current, so there's a lot of parallelism in current processors. So even if you are not aware of it, with pipelined vector processors, you are actually doing pipelining. So a single instruction, multiple data is a model in which that the same operations are run on parallel on a data vector. So even if you have only one processor that does the floating point operations, there are these pipelined instructions, and there are multiple processors often available on any ordinary processor. Okay, so it generates a plan. So this is where the plan comes in, which I glossed over when I introduced. It might have seemed rather artificial, but in the planning stage, there are the selection of the best data structures that are executable data structures that are being run on a very particular processor. So here one sees this is not a compute bound operation, this is a memory bound operation, and the preparation of the data specific for the processor is very important here. Okay, so let's look into sorting, and let's look into distributed memory. Data sets are often huge, and one reason to start using distributed memory processors is simply because the data sets are so huge to be kept on one single processor. One can also think of a data archival mechanism, and for that a pipeline is extremely useful. Okay, so bucket sort. Bucket sort distributes the data into buckets. Obviously here the buckets will be stored in a distributed fashion. We have P buckets, as many buckets as we have processors. So the big advantage here is that there will be, of course, communication overhead, but the big advantage here that each processor might be able to hold the bucket in its random access memory. Otherwise, the memory would need to be stored on the swap space or also on file, so which is consistent, which actually leads to a considerable increase in time. So the algorithm is very straightforward. It partitions, it sorts. Any sort you of course like, and of course we use quicksort, the built-in quicksort, to sort the buckets. So the purpose of this slide is that it provides also a very good paper and pencil exercise for a computational science prelim. So the computational cost is the sorting of the buckets. Each bucket has size n over p. And then the partitioning of the cost. So there's the partitioning, which is n log p, using, for example, the radix sort, using the first significant bits, and then the quicksort. On each bucket, we have n over p times the logarithm, the 2 logarithm of n over p. So but then we have to multiply again with p, because all the sorting of the buckets that are being done. So this is the sequential cost at the bottom. Let us now compute the parallel bucket sort. So this is a manager-worker paradigm. The root node is going to distribute the buckets. The root node is also going to sort, so the P processors here includes the root node among the P processors. So 3 stages in this algorithm: distributing, sorting, collecting. Now, let's now examine if it's going to be worth it. First, recall the serial cost. Then we have the parallel cost. So there is the extra overhead of the distribution. So that's the n log p factor. But then the timing to sort is no longer n log, the 2 log of n over p, but it's now really n over p. So we have that n over p factor. So we can compute that the speedup factor, it's kind of, so we have the serial cost in the numerator, the parallel cost in the denominator, and then we can simplify this with this 2 log factor, the L factor. So that is the most convenient expression that we can get for the speedup. So again, this is a great paper and pencil exercise. Okay, let's now interpret this formula. So that was actually missing from the previous slide. And actually this is still a continuation. So the L was kind of distractive. I think I used the L simply to make sure that the typesetting was right. But we have here now the speedup P over P plus L factor. So let's compute what it actually is. So here are some simplifications. And you can see that if you have 1,000,000 numbers to sort to the power 20, with 4 processors, then you get to a speedup of about a factor 3. Which is not too bad, but you can see the ratios between the size of the data and the number of processors. Okay, that was only the first part, so one side of the coin. In distributed memory, we have to be worried about the communication overhead. So let's compute the communication overhead, again also with the tools that we have seen earlier in the course. We have the startup cost and the cost that it takes to send the data. That is actually the time to distribute and collect. So there is the factor 2 that comes in because we have it at the beginning, the distribution of the data, and then we have the collection of the result. So what is now the communication over the computation ratio? We have to have some units there. In the numerator, in the expression, we have the parallel time. The units there are expressed in the time it takes to compare two numbers. In the denominator, we do have the communication costs. So in some sense, if this is a paper and pencil exercise, this is half of the solution. Let's now interpret this. Let's try to simplify the ratio, keeping in mind that the size of the data has to be significantly larger than the number of processors. It doesn't make sense to sort 10 numbers by 4 processors, for example. No, we're thinking about millions and billions for n and a relatively modest number of processors. Okay, so we have the ratio, if you look at now the leading dimension, so the n over p, let's drop this, or actually we have the n over p in the numerator, so we can simplify that away. In the denominator we have n divided over p, so we keep that as kind of the n over p as the factor. So we have the n over p times the 2 logarithm of n. So the 2 logarithm of n will actually be larger than the 2 logarithm of p. We can actually neglect also the 2 logarithm of p. So that's also what the last wiggling away is. Okay, so what does this mean now at the very end? So regardless of what the comparison costs versus the costs for sending a data element is, so suppose that you take this both to be the units, or you go to dimensionless constant, so you look at the ratio t compare over 2 of time for data or time data over time to compare, then actually the critical factor here, so at both left and right you have the n factor. What distinguishes the two, so we can simplify the n in this expression, is the 2 logarithm of the size of the data. And that should actually be sufficiently high. So you can see that even for a billion numbers, if that's 30, if it takes still 30 times more time to send one data element than to compare two data elements, then one is still not better off by a distributed memory sort. Again, in practice, this will also be very much related to the size of the available random access memory. If you have nodes with 256 gigabyte or 1 terabyte of random access memory, then that will actually determine the size of a bucket. So in practice, that will be it. By the way, this is also an example of a hybrid MPI and OpenMP exercise, or distributed memory versus shared memory parallelism. So this is a good combination of bucket sort. Bucket sort gives a good hybrid combination between the two. Okay, last part is quicksort for shared memory. How can you improve on that? Well, how does quicksort work again? So in some sense, I've mentioned quicksort, and this is an applications oriented lecture. Quicksort is so important that it is built into the language C. And actually here I'm using one very straightforward description to indicate what quicksort does. It partitions and it then sorts the two parts. It partitions the sequence such that before the pivot all the elements are less than what is after the pivot. So this is an in-place sort as well. So the cost is actually done in the partitioning. Here is the partition function where we swap items. So this keeps the lecture very self-contained. I will not go through the incrementing of the indices, so the up and the down. So they give the current element, so you start with the lower and upper bounds and you initialize the indices, and then as long as the two indices so the invariant is that the elements at lower and upper they actually should be less than the pivot. Everything the loop will continue to swap elements as long as the elements in the first half are less than the pivot, are larger than the pivot. If there's one element in the first half larger than the pivot, then it will swap. Actually a very simple algorithm. So C is our language. If you're unfamiliar with C, then this is a great opportunity to see more of the syntax. I also gloss over the fact that quicksort is n-log n. Notice that here you see a double loop. In the worst case, quicksort is quadratic. So on average, it is n-log n. But you can see from the double loop that there are sequences that make it quite bad. Okay, this is a do-it-yourself programming. So I'm actually not using, or actually here I am using the quicksort that is built in. So I'm doing the partitioning with the code, but from the qsort by using the void, using the compare operation, and then also the size t. I see that I have used the built-in quicksort function. So we have the quicksort, and now we can do the quicksorting in the parallel region. Simply with two threads, I wrote this exercise just to see what would happen if I have a multi-core, a dual-core laptop. Can I speed this up? And of course the answer is yes. This comes from the early runs of the course, where I was still very, very happy with the good results that we got with a very plain application of OpenMP. So here we are sorting 1 million numbers. First, sequentially takes 4 seconds. Then if we are doing this in parallel, it takes 3.7. So 4.2 to 3.7, it's 13% faster. Which is good given the very little extra code that is required. In a way, a lot of the things that we are doing here are kind of counterintuitive. Sometimes to get good parallel code, significant rewrites are needed. Okay, stopping with Intel threading building blocks. Intel threading building blocks actually do have built-in parallel sort, and here it is. So of all the C code that we have seen so far, this is actually the recommended way of working. So it's essentially also C++ code. So we have the using namespace TBB. We include the proper header file, the parallel sort, allocate for numbers, parallel numbers, and then we call the parallel sort. This is C syntax. So the first argument is the start of the array, and then we do the pointer arithmetic. V plus n gives the end of the array. Okay, just to make sure that it works, so the interactive sorting of numbers, 4 numbers, the one here indicates that we have the, we want to see the output, this is for testing purposes. Okay, and now let's do the timing of the parallel runs. So this was still done also with the 2 × 8 core machine, 16 cores. What is so good about this, I'm actually starting from 1 million numbers, or actually more if I count the number of zeros. I have 10 billion, 100 billion, 10 million, 100 million, 1 billion numbers. So the point being that each time I'm multiplying the size of the input by 10. And this is an illustration of also what it means to be quasi-linear. It's actually linear, and this is again a manifestation of superlinear speedup. So with 1 billion numbers, 2 to the power 30, you would expect actually the factor 30 to start creep up in the n log n. But what you see, we have the real time, the wall clock time, 4.7 is 47.4. So the sorting, the parallel sort here, behaves as it is linear as far as the wall clock time goes. You see that the user time actually significantly increases. What that actually means is that the CPUs, so the dual core, 16 cores in total, are actually working extremely hard here. Also, the system time is already quite, the system is quite busy with the allocations of the memory. So this is one sequence of 1 billion numbers sorted in 47 seconds, starting from 479 milliseconds, half a second to more than half a minute, so you could say as well. Okay, so this is the second time that we witness super linear speedup. Okay, here are the references. So sorting is an extremely important problem. Here are several of the papers in the supercomputing languages. SPLASH is actually the conference on object-oriented programming languages. I think it's also called OOPSLA. So there are the other IEEE conferences, and then there is the paper on the fastest Fourier transform in the West. So part of the purpose of this course is that one gains access to the literature, that several of these papers are very readable for you, and also of course is that you can work with this. So supercomputing is also in this course parallel computing. We've seen paper and pencil exercises for those of you who take this course with the eye of a computational science prelim, which is run in the traditional fashion, paper and pencil. Then there are some great exercises here to, for example, consider the fan-out algorithms. Now, of course, in this context here, we said that the number of processors should be fairly limited. But now imagine that you are really on a big, huge supercomputer with thousands of processors. Then it still makes sense to consider the fan-out and gather-in operations, which we have seen earlier in the class, which operate at a cost that is logarithmic in a number of the processors. The Intel threading building blocks, there is the one API that we have covered. Also, I've mentioned Julia, but I have no Julia code listed here. We have covered Julia before with recursive tasking. So in some sense, this course comes back to that again. So some of the exercises you can definitely also do, or you have already done, with multitasking. So in the next lecture, we will consider parallel linear algebra.